Hey everyone, this is Dr. Iad. I'm noticing that some of us are having some questions about how to fill in the Hydrate design worksheet. Many of us haven't quite gotten to molar masses yet in our lecture classes. It's kind of normal that in the summer semester the schedules don't align quite right. And so I'm going to go through some of the basics of how to find and calculate the molar masses for things, and then how we're supposed to fill in this table and what it's supposed to help us figure out for our lab video. Now, this week's activity, we are taking a salt. So a salt in chemistry is just an ionic compound. It means that it's got a metal, it's got a non-metal, and oftentimes it'll also be kind of wet. Now, not wet in the sense that it's dripping with water, but wet in the sense that it has moisture absorbed into its crystal lattice. And so water can kind of get stuck inside of these compounds, and it stabilizes the compounds. So if we're trying to figure out exactly which hydrate we have, we're going to have to heat it up, add some chaos to the mix in order to liberate that water. The way that we're going to use that to help us identify these materials is if we can figure out what percentage of each salt is water and then liberate some amount of water from a known mass sample, then we can figure out which one of these four theoretical percent masses of water corresponds to our real life sample. So let's get into it. The molar mass of a substance is how much mass it has per 1 mole of that compound. A mole is just a very convenient way for chemists to relay how many atoms or molecules there are in a substance. As you can imagine, atoms are really small. And so a mole represents a huge number of those atoms. If you haven't gotten to it yet, we use Avogadro's number to calculate the number of atoms or particles in a mole of something. Now, a mole is kind of like a dozen or a gross of something. It's just a number of anything. And so you could technically have a mole of grains of sand or a mole of stars in the universe. That's the way that we're using mole here. Now, the molar mass is a ratio. It's telling us how many grams of the substance there are for every X number of moles. For convenience sake, since moles is on the bottom, we always set it as 1. And so we're looking at grams per mole of something. Let's see here. We are looking at grams. Whoops. Sorry, I'm still getting used to my new tablet here. Okay. We are looking at grams per 1 mole. And the number of grams is going to vary based on the atomic masses of the elements that make up our compound. Let's go ahead and figure out what the molar mass for water is going to be. And so water is made up of H2O. The H represents the atom hydrogen. The subscript 2 tells us that we have 2 of that hydrogen atom, and the oxygen there, that single O with an implied subscript of 1, tells us that we have 1 oxygen. In order to figure out what its molar mass is, we're going to take a look at our periodic table. So I have a periodic table pulled up here, and it tells me that the atomic mass of hydrogen is 1.008. So I'm going to go ahead and write that down here, 1.008. And we can represent this with either the units of AMU, which is short for atomic mass units, or we can simply write it as grams per mole, because quite conveniently, we have defined 1 AMU as 1 gram per mole. Most of the time, we're going to be using grams per mole and not AMUs moving forwards, because these are values that we can work with in the real world. All right, so that's the weight of 1 hydrogen atom. Since we have 2 hydrogen atoms, I'm going to take that 1.008 and I'm going to multiply it by 2 because we have 2 of that atom. And then I need to know how many AMUs, or grams per mole, oxygen weighs. Taking a look again at the periodic table here, I see 15.999. Moving back over, we've got 15.999. If I've followed through on this calculation, it should tell me how many grams per mole the molar mass of water is. And so let me just grab my off-screen calculator real quick here. 2 times 1.008 plus 15.999, and we get 18. Let's see here, 18.02 grams per 1 mole. Now, many of you might be looking at that value and saying, whoa, 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 Dr. Ayad, you forgot some decimals there. Well, it actually turns out that I'm just applying the sig figs rules that we learned earlier this semester, where hydrogen is measured to 1, 2, 3, 4 degrees of certainty. And so even though the oxygen has 5 degrees of certainty, I'm limited by my least certain value here. And so that's why I represent this as 4 significant figures. Now, that's the molar mass for water. And that's going to be a pretty important value for us. So I'm going to go ahead and write that down back here at the top so we can reference back to it later. We had molar mass of H2O is equal to 18.02 grams per 1 mole. Now, looking back at my Hydrate design worksheet, I'm given some sample calculations. They've told us what the molar mass of our anhydrous salts are. Now, anhydrous just tells me that it's without water. And so looking at the first example here, BaCl2 with 2 H2Os in it, well, the anhydrous version of that salt would just be the BaCl2. So we've just done some of the weirder calculations for you there. We added 1 barium and 2 chlorines together to come up with 208.28 grams. Similarly with the copper sulfate, calcium chloride, and zinc sulfate, those are just the molar masses for those without the waters. Now, in the first one, we've found the molar mass of NH2O to be 36.04 grams. N in this case, and often in chemistry, is going to represent the number of moles of something you have. And so, since we have 2 H2Os as part of this hydrous formula here, we're multiplying our 18.02 grams times 2, and that took us to the 36.04 grams. And so, in the next part of my calculation, we're looking for the molar mass of the hydrate. Well, it stands to reason that the molar mass of the anhydrous salt plus the molar mass of all of the waters in that salt should be equal to the molar mass of the hydrated salt. So I'm just going to be adding together the 208.28 and the 36.04. 208. Sorry, I've got a terrible memory while I'm speaking. 28 grams per 1 mole plus the 36.04 grams per 1 mole is equal to the molar mass for my hydrous salt, 208.28 plus 36.04 gives me 244.32 grams per 1 mole. The reason this value is useful to us is because it's going to allow us to figure out what percentage of the total thing is water. And so in order to find a percentage of anything, you want to think of it in terms of the part Whoops. Oh, God. Again, still figuring out the new tablet. All right. We got, oh, nope, that didn't fix it. You know, I'm definitely leaving all these bloopers in despite not speaking to a live audience. You're welcome. Whoa. And come back. Oh, and it just deleted it for me. Nice. All right. So anytime you're thinking of a percentage or any kind of a ratio of something, you want to do it as the part, meaning the smaller portion, over the whole, meaning everything you've got. This is coming up in some of our homework assignments in my lecture class, where you want the small thing over the total thing. The small thing in this case is going to be the amount of water molecules in this particular compound. And so we're going to say that is the 36.04, and we're going to divide that by the whole, which is the anhydrous salt plus those water molecules, and that's going to be my 244.32. You might notice I'm leaving units off here. While technically you should include them anytime you're doing work and calculations like this, these units are going to cancel out anyway, because all percentages are by nature unitless. And so when I do this on my calculator, 36.04 divided by 244.32, it tells me that I have 0.1475 of my compound here. Now, you can do the times 100 earlier or at this point. Percent literally translates to per 100 of something. And so it doesn't really matter where you put it in here, but to represent it as a percentage, it should be 14.75% H2O in BaCl2.2H2O. So that's how you do one of these calculations. I'm going to go ahead and walk through one more of them with you. All right, back over to our worksheet here. Let's try for the copper sulfate. They tell us the molar mass of the anhydrous salt is 159.58. All right, 159.58 grams per mole is the molar mass of CuSO4, copper sulfate. Now, this is the molar mass of the copper sulfate without the water. We want to figure out its mass with the water. To start, I got to figure out, well, how many water molecules are there? Simply looking at the chemical formula, we see 5H2O. And so I'm going to come back over here, put a 5 times, and I need the molar mass of H2O. Forgive me for not showing the calculation a second time here. But previously, we found that the molar mass of water was 18.02 grams per 1 mole. And so the molar mass of all those waters added together is going to be 90.10. Now, I'm choosing to include 4 significant figures here because 5 is an exact value. Exact values don't factor in when you're doing significant figure calculations. I know exactly there are 5 of those things. It's kind of like counting money. The value I got on my calculator was 90.1. So I added a 0 on the end to say, yes, it is specific to this exact value. Okay. And of course, we can't forget our units yet here. That's grams per mole of NH2O in that compound. For the next box, I'm adding together the molar mass of my anhydrous salt plus the molar mass of my NH2O. And so 159.58 grams per 1 mole plus 90.10 grams per 1 mole. And I get 249.68 grams per 1 mole is the molar mass for my hydrate. Molar mass for the hydrate. MM just to abbreviate molar mass. And now the last part of our calculation, we want to find the percent water in the hydrate. So what I'm going to do is take the molar mass, put it on the bottom, the denominator, and I'll put the mass of my H2O on top. Multiply this by 100 so that it's represented as a percentage. And I end up with 36.09% water in that sample. The way we're going to use these values during our lab this week is we're going to fill in all the percent waters. And our experimental question is something like, how can you figure out, which of these hydrates it is? By using our data that we collect during the lab, taking the mass of the salt, taking the amount of water that was liberated from it, and then calculating the percentage of water, we should be able to try and match the amount of water lost to these percent waters in the hydrates that we calculate on this worksheet. And so theoretically, one of the numbers should be closer to the percent water you lose than any of the others, and then you could make the assertion that, well, it's probably that substance. Don't be afraid to use other observations or data that you gather through the course of doing these labs. I know we're doing it virtually here, but feel free to look up information about colors or consistencies or anything else that might help you in making a determination about which one of the substances it is. As always, please visit me in office hours. Please email me if you have any questions. Thanks everybody that got that first rough draft turned in on time. Yeah, I look forward to hearing from you. Keep up the great work, guys.